Good morning, everyone. So today we'll look at the third IMO from the year 1961, and this one was held in Hungary. Okay, so they have six problems, and let's go through them. So this one, it says there's a system of equations: x plus y plus z equal to a, x square plus y square plus z square equal to b square, and xy equal to z square. A, b are constant, and it says give the condition on a and b such that x, y, z are distinct positive numbers. Okay, so first of all, what do these equations represent? So this is a plane, right? So this equation, it represents a plane with the cut on the xyz axis is equal to a, and the distance from the origin is a by root 3. Okay, so how do you calculate the distance from origin? It's just this divided by the square root of the coefficient. So it's square root of 1 square plus 1 square plus 1 square. So it's a by 3. Okay, and what's this one? So this is a sphere with radius mod b, right, and center at origin. So this represents a sphere, center is at origin, radius is mod of b. This one, let's not worry about that. So if we are looking at the solution for this, so we are looking at the a plane where it cuts the sphere, right? So that's a part of the solution. So if you want to sort of visualize it geometrically, and since x, y, z are positive, it's given, so we'll just look at the first octant where x, y, z are all positive. So this one is like 1/8 of a sphere, and then there is a plane which goes through that, and the intersection of that's a circle. That will be can be the solution for these two, right? So if a solution exists, what should be the minimum condition? So this distance of the plane. So if the plane becomes tangent to the sphere, then there will be just one solution, right? And if the distance from the plane increases the radius of the sphere, then there's not going to be any solution at all. So one condition is that a by root 3 should be smaller than mod b, right? So in order to have an intersection. But of course, we also want the cut to remain in the first octant. So in case the cut of the plane becomes smaller than b, smaller than the sphere cut on the axis, then again there will be no solution. So how do we represent that condition? So the plane, when it goes through the cut of the sphere, the distance will be what? It will be mod b by root 3, and the distance of plane is mod a by or a by root 3. So the minimum condition is this. So mod b by root 3 is less than mod a by root 3 is less than mod b. So this one is for the lower half when the plane cuts the sphere at the axis, and this one is when it is tangent at the upper half. And we of course we don't need the equality here, because if it's equal, then of course you can see by symmetry the intersection point is going to be x equal to y equal to z. Okay, and on this lower half, when there is equality, so two of the components will be 0, right? So we don't want that, so we have strict inequality everywhere. So this is a necessary condition. And after that, let's worry about this equation. So let's see what happens if x equal to y equal to z. Can we have a solution like that once this is achieved? So of course, if x equal to y equal to z, we'll get 3x equal to a, we get 3x square equal to b square, which will give you a square by 3 equal to b square. So which means this one, and of course we don't have the equality here, so this is not possible. Okay, so let's say two of them are equal and third is not equal. So when x is equal to y, but they are not equal to z, what happens then? So is this condition possible? So let's say you just put it in this one, in this third equation. Y you put it to be x, you will get x square equal to z square, so that gives x equal to plus minus z. So if x is equal to z, then you get x equal to y equal to z. If x is minus z, then of course you get x positive, so that will be make z negative. Okay, and we don't want that. We want all positive. So this is not possible. If you look at x equal to z and not equal to y, so this one you make x equal to this side. So you get xy equal to x square, and that gives you solution x equal to 0 or x equal to y. X equal to 0 we don't need because we need it positive, and of course if x equal to y, then all are equal, so that's not possible. And again, if you look at the symmetric case where y equal to z and not equal to x, then again you'll get same thing, y equal to y, or y equal to x or y equal to 0. So all this is not possible. That means x, y, z are all distinct. So as long as this condition holds, this one, x, y, z have to be all distinct. So this case is also sufficient. So this is your required condition. Okay. So this problem says ABC are sides of triangle, T is the area. So prove this relation. So there are many ways to do it. So this is a triangle. So you take the largest angle, you draw a perpendicular from that. So that's one way of doing it. Of course, when that happens, it will, that will make sure that this x and y are positive. So now you write the relation this as, take this one as a, take this as b, take this as c. So a square will be x square plus h square, b square will be y square plus h square, and c square will be x plus y whole square. C is x plus y. And the area is half of x plus y into h. So you get that, and you make it a quadratic in h. And then you complete the square and you write it as a sum of two squares. So of course, if it's sum of two squares, it has to be greater than or equal to 0. And then it's asking for when the equality holds. So when equality holds, this will be 0, this will be 0. So x is equal to y, and it will give h equal to root 3x. So this will make this angle 60 degree, this angle 60 degree, and it will make the triangle equilateral. Okay, so yeah, that's it. This is problem 3. It says solve this equation, cos to the power nx minus sine to the power nx equal to 1, where n is the natural number. So first of all, if n is even, then you can write cos to the power nx is 1 plus sine to the power nx. And since this is greater than or equal to 0, this will be greater than or equal to 1. And since cos x cannot take a value greater than 1, so then there has to be equality here. And this can hold only when sine x is 0 and cos x is plus minus 1. Okay, so that happens when x is equal to k times pi, where k is an integer. And the next case when n is odd. So for odd, we have to take n equal to 1 separately. You take n equal to 1, and then you can basically convert it into half angle. You take 1 cos x as 1 minus 2 sine square x by 2, and sine x as 2 sine x by 2 cos x by 2 equal to 1. So 1 gets removed from both sides, and you have the two products equal to 0. When this is equal to 0, sine x by 2 equal to 0, you have one solution. When this is equal to 0, you have another solution. Just write it down. So this will be equal to k pi, so x will be 2k pi, and similarly this will be equal to k pi, then that gives equal to 2k pi minus pi by 2. So when n is greater than 1, then I write 1 as sine square x plus cos square x. Then you rearrange it. And what you need to notice is that this and this, they will always be both greater than or equal to 0, because it's all minus cos x and sin x. They will all vary between minus 1 to 1, and then you add 1 to it, so it will all be above x-axis, or above y-axis. So this happens. So then if this is 0, then individually they have to be 0. So if cos x is 0, then this cannot be 0. So this has to be 0. If sin x is 0, then this has to be 0. Okay, so you look at those two cases. So if cos x is equal to 0, then sin x has to be minus 1. That gives one solution. If sin x equal to 0, then cos x will be 1. Then that gives one more solution. So since you have a multiple of 4k, you would like to write it as a multiple of 4k. So the solution is that when n is even, x is equal to k pi. When n is odd, x is equal to this, because this solution also fits in this one. Okay, so that's your answer. Okay, this is next problem. It says there's a triangle P1, P2, P3. P is a point inside the triangle, and from the vertices you draw lines through P. So P1P, P2P, P3P, and they intersect on the opposite side at Q1, Q2, Q3. And you have to show that one of these ratio is less than equal to 2 and one is greater than equal to 2. Okay, so this is, yeah, it's actually a simple problem. So take this triangle and look at its centroid. Yeah, so this centroid, if you draw a line through this, it will divide that line into 2:1. And if it happens that P, if it lies below this, then this P1P by PQ1 is going to be greater than 2. If it's above this, then it's going to be less than 2. So the best thing that you can do here is that you look at lines which are parallel to the sides. Okay, you draw lines, this one parallel to this one parallel to this one parallel to this. And now let's say if all three ratios are greater than equal to 2, what happens then? So if this one is greater than equal to 2, P1P by PQ1, then this P has to lie below this line in this region somewhere. So P has to lie in this region. Okay, if P2P by PQ2 is greater than 2, so from this, if you draw that, if it's greater than 2, then P has to lie on this side of this line, on this side. Okay, here. So P can lie on this, from this condition and this condition, P has to lie on this darker area here. But of course, P3P and PQ3 is also greater than 2, then from this, if you draw it, it has to lie on this side of this segment, so it has to lie here. But of course, you cannot have any intersection with this region and this region, so that means there is no possibility for any P. So this case, all three greater than 2 is not possible. So sum of the ratio has to be less than equal to 2. Okay, and in the same way, you look at what happens if all three are smaller than 2. If this is smaller than 2, then P has to lie now on the upper side here. If the second ratio is smaller than 2, then it has to lie on this side here. So basically that means now P has to lie on this one, the intersection of two regions. And if third one is also less than 2, then P has to be on this side here. So P has to lie on this region. But of course, the intersection of this one from this is nothing. So that means a P is not possible here. So to satisfy all these three conditions. So P cannot satisfy all these three conditions. So sum of the ratios has to be greater than equal to 2. So this is not possible. So there is at least one which is less than 2, and then there is at least one ratio which is greater than equal to 2. Okay, so that's the solution. Okay, so now this problem 5, it says construct a triangle ABC if AC equal to B, AB equal to C, angle AMB is omega, and where M is the midpoint of BC and omega less than 90 degree. So something like this. So this is given, and the angle that AMB has at the midpoint, that is given. So how do you construct it? So since this angle is fixed, then M is going to lie on a circle. So what you look at is this. If you draw a midpoint from this, okay, so the M lies on this circle, and of course the second thing is that if you join the midpoint of this to this is going to be exactly half of that. So this length is B by 2. With this information, now you can construct it, right? Okay, so let's see. So you draw a line segment AB of length C, and you draw a perpendicular bisector of length C over tan omega by 2. So now you can see that this angle here, if you join this, it's going to be omega by 2, and this one is going to be omega by 2 here. So you have these 3 points, and now you can construct a circle around these 3. So maybe you can just join these 2 and take a perpendicular bisector, you will get the center, and once you know the center, then you just extend the radius to one of these points and you draw a circle. So your circle is done. After that, what you do is you take a length B by 2 and you cut off on one side or maybe both sides, but it will, since there is a symmetry here, it will just give you 2 triangles which are like mirror image of each other. So I'm just drawing it on one side. So this is it, and Of course, M is the midpoint of BC, so you take BM and double it, extend it on this, and you get your triangle ABC. So this length is going to be double of that. So this is B. So this is that, and now it's asking you to prove this relation. So what is the value this b by 2 can take? So b by 2 can take a maximum value of this c over 2 tan omega by 2, and b by 2 can take a minimum value of c by 2. But of course, when it goes to c by 2, here it cannot reach the equality, because then the triangle will be degenerate. B and M will coincide. But here M can go to this point. So you have this b by 2, it has to be greater than c by 2, strictly greater than c by 2, this one, and it has to be less than equal to this. And then you can rearrange it and you can get your relation. You bring this to this side, this to this side, you get c greater than equal to b tan omega by 2, and from this you get c less than b. So you just rearrange it and you get your relation. So, and now it's asking you what happens when there is equality. So when there is equality, then M will reach this point. So what happens when M reaches here? When M is this point here. So let's just draw it again. Take M to be this point. Take BM, double it, and this is your triangle. So what kind of triangle is this? So you have this equals this, and of course this is also equal to this. So if you draw the circumcircle of this triangle ABC, so these three are equal. So that means this point A, it lies on this circle which has BC as diameter. Okay. So what does that mean? So that means this angle BAC is 90 degrees. So triangle ABC is a right triangle when there is equality. Okay, so that's your problem 5. Okay, so this is problem 6. It says there is a plane epsilon, and then there are 3 points, non-collinear points on the same side of epsilon. So you take epsilon to be z equal to 0 plane, and take the other points ABC on the z greater than or equal to 0 side. Okay. So I'm not trying to draw a diagram here. It's quite simple. If you want, you can just draw the diagram. X, Y, Z axis. Take z equal to 0 plane in the XY axis, and take ABC on the positive side. And of course, yeah. So, and then it says what? Okay. These points. So it says these points are not parallel to epsilon, and then it says in plane epsilon, take 3 points A dash B dash. 3 points in the plane epsilon. So let's take the coordinates of ABC as A1, A2, A3, B1, B2, B3, C1, C2, C3, and it's given that, of course, this Z component is going to be greater than 0. So A3, B3, C3, they will be greater than 0. Okay, and take A prime, B prime, C prime. So this should be primed. Sorry about that. So take its coordinate to be A1 primed, A2 primed, and 0. B1 prime, B2 prime, and 0. C1 prime, C2 prime, and 0. Okay, because since it's lying in this epsilon plane, the Z component is 0. So the Z component here is going to be 0. And then it says LMN are the midpoints of the segments A prime, BB prime, CC prime. You find the coordinates of LMN. L, the x coordinate is going to be this plus this by 2. Y coordinate is going to be this plus this by 2. Z coordinate is going to be this plus this by 2. Same for M. Same for N. So you have the midpoints of this. And it says G is the centroid of LMN. So you take the centroid. So centroid is going to be this plus this plus this. And there's 1/3 of that. Y component of centroid is going to be this plus this plus this, and 1/3 of that. Z component of the centroid is going to be this plus this plus this, and 1/3 of that. Okay. So you just write the centroid of element. This is what it has, and just if you want, you can rearrange it. And what does it ask? Just one sec. It's asking you what is the locus of G if A prime, B prime, C prime range independently over the plane epsilon. So if A prime, B prime, C prime, when they vary, what is the locus of G? That's what it's asking you. So Just go ahead, you find the coordinate of G. You can rearrange it if you want, just to have a look at that. Locus is actually the midpoint of the centroid of ABC and A point, B prime, C prime. Okay, and this is the variable part here, the prime coordinates. So this, when this varies all over the plane, so these two components will vary all over, but this remains constant. Okay, so these two components vary, and but the Z component is constant. So the locus is basically a plane. Coordinates are 1/6 of A3 plus B3 plus C3. Okay, so this is your answer. Okay, so this was the third IMO. I think it was. I think the problems were slightly simpler than the first two IMOs. I mean, just slightly, not like not too much. It's almost the same level, but just slightly simple. I hope you enjoyed the solutions, and thanks for watching, and I'll see you next time. Okay, bye.